You see, I work tie-dye in solidarity with my secretariat because they work they suffer most of my hands all week. I want to be there for them. Yeah, well, you're one of these byproducts of this. They're not non-chronological. So they're competition.
Ja, det är jättesäkert. Mitt flyg, sms igår, mitt flyg är inställt. Men det var ju samma flyg som kommit till den. Det slog jag från 6 istället för 9 istället.
Det är lite olika.
Men har det blivit mycket till så? Ja, det är men jag tror det bästa man kan göra. Man är rädd bara för att sen så görs det där inget konstigt.
Det är lite som
ja. Nej, men det är det. Alltså, det är ju det på jag ska skriva privat till mig. Ja, precis. Det går jättebra. Då kan vi göra det. Det är superbra. Man kan inte ta det ut som ta med något fel så ska det avgränsat enkelt och inte konsumerat inte konsumerat space. Allting går avgörande. Det är liksom det gäller bara att veta om det kickstart tillräckligt bra. Ja, det blir de lite exakt, precis. Och om de slutar lite eller vad de kan de göra det next week. Precis, hur använder vi det? Det kommer
Hi, good morning, folks. If you haven't read this article, you should. It's a lot of fun. I'll start off with that. It's a lot of joy and fun. You should read this with a lot of popcorn or with scotch, your preference, but it's fun. I'll move on. Go search for it, humming an open internet noise. It's just fun. So we're going to start the ICCRG meeting in IETF 101. Thank you all for being here early in the morning. I know it's Friday and it's early in the morning, so we'll try to keep this short and sweet. Before we start, we need a few people. You know the standard questions. Raise your hands now if you want to be a Java scribe. Don't make me choose. Somebody, JavaScribe. Thank you, sir, Matt. I need one more person for minutes. And I have a link here for to use Etherpad so people can contribute. So you won't be the only person taking minutes, but I need a point person. We can do a crowdsourcing experiment too. Silence. It's like nobody can hear me. I can say anything right now. Minutes, minutes, minutes. Michael, why aren't you raising your hand? It's been a long time since you took minutes in ICCRG. Somebody, minutes, please. If you don't take minutes, I'm going to spend 5 minutes asking the question of should we stop taking minutes in this meeting? Because it's really not a meeting. I don't mind doing that, having that conversation either. Are you going to take minutes? Thank you, sir. You just avoided this conversation. So welcome again. We'll start quickly. I'm going to hand out blue sheets in a moment. Please sign it. Please add your name and your affiliation to it. In the meanwhile, you can all read the note well. I'm sure you've never read it before, so take a moment to read it.
It's you.
If you haven't read the note well, you actually should read it. It's about IPR disclosure and IETF participation, and it applies to this meeting. So please make sure you can look for IETF note well, and you will find this. That's about all I'm going to say about this for now. So if you haven't read it, please go read it. Here's the agenda, but I think there's at least one modification that I know of. We're going to have Paul. Paul, are you in the room? There you go. Thank you. Presenting some initial proposed IEEE standardization work, which Paul and others who are proposing this in the IEEE thought would be of interest to this room, and they wanted to basically give a short bit summary of the work that they're proposing there. So we're going to start with that, and then Ingemar is going to talk about BVR congestion control and L4S support, especially for 5G networks. Neil will give an update on what Google's been doing with BVR in the past 4 or 5 months. Praveen is bailing on me, so I'm going to call him out. Where's Praveen? I'm not going to call him out. I want Praveen to present LEDBAT++, and he will hopefully do that again in the future, but he's not going to be able to do it today. So that's off the agenda. And we have Michael Shapira from Hebrew University to talk to us about performance-oriented congestion control. It's an exciting and a different form of congestion controller than we've seen in the past, and I'm excited to have him here. So I hope that generates a fair amount of discussion. I'm not going to close that one very quickly because I think we're going to have time today to spare. And then we have a very short presentation on a new idea for doing congestion control in bandwidth guaranteed networks by Yingchen. So we'll just show up when it's time for your presentation. In the meanwhile, if there's nothing that you want to bash on the agenda, we'll start. Do you want to start, Paul? That is, I can try. No, yeah, I'll advance. That's probably the best thing.
Okay, just real quickly, show of hands. How many people were in TSVWG? Okay, so this is the Cliff Notes version of the presentation I did yesterday. So we'll, but I think I may have some clarifications on the some of the comments or questions as well. So, as mentioned, we have a proposed project in IEEE 802.1 for congestion control algorithm, or congestion management algorithm, I guess I'd say. It's proposed, meaning it hasn't started yet, but it has is in the process of approval. And one of the things that we need is more review and feedback. And because it's intended to cooperate with congestion control from the IETF, we thought it was very important to do this presentation. So next slide, please. So back in November, 802.1 agreed to create a project authorization report. That's a proposal. It goes through various levels of approval, and ultimately the working group votes to create that project. So we decided to delay this project until July timeframe in order to obtain more simulation data, more approval, more review from others. So again, this is why I'm here. The motivation for this activity is documented in a report, a pre-standardization report from the IEEE 802. The link is here. This is an open process that involves end users and standard and vendors to kind of define the requirements of the next generation data centers. So have a read of that and send me comments. So that's where we're at. So what is this thing we're talking about? Next slide, please. So first of all, we are amending 802.1q, which if you're familiar with 802, that is the book that describes Ethernet switching, which is really the foundation for chips that are used in routers, data center switches and routers today as well. So it's all sort of related. And the scope of this project is specific to data center environments, so within the data center. So we're not talking about across wide area links. And what we're doing is we're trying to isolate flows that are causing congestion in these environments, like Rocky V2 or high performance data center computing, kind of artificial intelligence types environments. So the way this works is that this bridges, but I'm calling them bridges because that's what our terminology. But again, fundamentally, they're layer 3 switches, routers. They have Ethernet links. The ASICs have effectively one set of queues on the ports, so they're all shared between the layer 3, layer 2 functionality. But what we're doing is we're going to identify flows that are creating congestion in the data center. And so a lot of questions came up about, well, how are you doing that? Well, one of the challenges we have in 802.1 is finding the right level of specification and allowing implementation flexibility as well. So we don't typically try to over-specify things. We specify behavior and whenever we can. And so we're assuming in this scenario that there's already many mechanisms that are in chips today that are identifying congestion, because you're doing things like marking the ECN bits. And so we're going to use those existing mechanisms, or we will use mechanisms that we have defined. So there are techniques in 802.1q. Nonetheless, you find the flows that are causing congestion. And for those flows, what we're going to do is adjust their scheduling, adjust transmission selection. So we're going to move them, so to speak, to a different traffic class. And then we're going to schedule and mix in that traffic class in a way that doesn't reorder packets, but it effectively delays those flows that are causing congestion, allowing the end-to-end congestion control loop time to react. So the concern is that as data centers get faster and bigger, that they're not going to be as reactive as we want them to be. There's going to be a lot of packets in flight with 100 gigabit Ethernet, and that we want to absorb those as we can, and giving ECN time to do its rate adaptation. So that's the high level. And another trick and reason why we want to standardize this is we intend to provide a signaling mechanism on a hop by hop basis to the upstream neighbor to identify those same flows. So that way that upstream neighbor can also do the same and provide the isolation that allows even a little bit more buffering. And so it can kind of propagate back. The hope is it never propagates all the way back to the source, but because we want ECN to do that. I'll explain more on that. So anyway, the scope is really about reducing head-of-line blocking for, separating the flows, the congested from the non-congested. And as I mentioned, it's intended to be used with the higher layer congestion control defined here. Next slide, please. So kind of the assumptions of the lossless data centers of today, the high performance computing, or again, storage, Rocky V2 storage environments, is that the network is a layer 3 network, first of all, that all these links and boxes are really routers, and the links between them are subnets. It's a CLOS network, fat tree, and we are using ECN as, our DC TCP, or Rocky V2 with DCQCN as an end-to-end congestion control mechanism. That may be application specific. So for Quick, for example, or for Rocky V2, that's more or less an application thing. If you want to create a purely lossless environment, there's the ability to use per flow or priority-based flow control. So in other words, pausing the frames and on a per class basis. This is often not discouraged, or a lot of times people don't like to do that because it creates head-of-line blocking. But that is your sort of last effort, last gasp to never drop a packet. If we're really running out of buffers and we don't want to drop, then we're going to do flow control. And again, these are all using typically code points as a way to identify the different traffic classes, and maybe as opposed to VLAN tags these days. Next slide, please. So 802.1 already has two sort of existing congestion management tools. I just mentioned priority-based flow control. So typically we have 8 classes of service, or 8 queues, if you will. You can define those queues to have individual flow control. And so that requires extra buffering, so that you have headroom. So typically people don't turn this on all the classes. They may turn it on one class or something like that. But again, the concern is that it creates like a head-of-line blocking scenario. So as I push back, I'm blocking the entire traffic class. So if I have multiple flows sharing that traffic class and they may be going to different destinations, I'm fundamentally stopping them all. So that's the negative downside that we see. That causes some buffer bloat, causes backup and congestion spreading. So in general, we see maybe priority flow control being used only at the edges to keep from overrunning NICs, not so much used in the core of the network. But if you want a truly lossless environment, that's sort of your last tool in the bag. Next slide, please. There's another approach that 802 had defined for non-IP type networks, if you will. So this is where your fabric is a big layer 2, and you're doing something like fiber channel over Ethernet, or maybe Rocky version 1, where you didn't have IP, you didn't have layer 4 congestion control. So we were trying to create a layer 2 lossless network. And here we actually signal a congestion message all the way across the layer 2 fabric to a source and have the NIC, so to speak, perform rate control itself. Again, that was sort of defined for these non-IP based protocols, didn't necessarily see a lot of use. There was a mechanism defined here to identify flows causing congestion. That's one of the mechanisms we could reuse for our proposal. Next slide, please. So congestion isolation. So first of all, the goal here is to work in conjunction with the higher layer congestion control. We want the stacks, the endpoints to do their rate adaptation in the way they do, but we want to provide assistance or more time for that control loop to work. And we are doing that by creating yet another control loop. So that's the tricky part. The goal is making bigger, larger, faster data centers that reduce loss or have no loss. Do this in a flow agnostic way. One observation is as we get faster links like 100 gigabit and higher port density, we're seeing less and less available memory in those switches on a per port, per pack, gigabit per basis. So we are pressure on switch buffers, so we can't just throw memory at the problem. And primarily reduce flow control and head-align blocking. So next slide, please. Okay, so just briefly, kind of unless you want, we'll wait till the end to take comments. Briefly how this is going to work. So imagine we have an upstream switch and a downstream switch. Obviously, we're going to have a full fabric here, and there's traffic coming from all directions, but just to simplify the discussion. So as in the downstream switch, as congestion creates, frames begin to queue in the egress of the switch, the logical or physical egress of the switch. There's some thresholds here at which point we will be detecting congestion. And this is where mechanisms that are being defined in IETF could be appropriate, or ones that we have already used. We're not necessarily specifying the specifics of that yet. That's an option. But once we've identified congestion and a flow that may be causing it, maybe it's sampling, we will remember that. We will keep track of this flow, and subsequent packets for that flow that are coming in, we will now queue in a different class, in a different traffic class. And we're going to schedule that class in a way that avoids out of order packets. But the key is that we're effectively sort of delaying that and using buffering in the switch to delay the flow that's causing congestion. Now, this might be an elephant flow statistically, but we don't know. But hopefully we've got the right flow. Next slide. Eventually, as that congested queue begins to back up, we want to tell our upstream neighbor so that we can use his memory as well. So this is where we would send a signal. We call it a congestion isolation message, which is effectively a message that includes the flow information, so the upstream switch can identify the same flow and will do the same thing. Next slide. So then that upstream switch will also be isolating the flow. And that's where we effectively now are eliminating head-align blocking. So the non-congested flows, the mice, the green, the good guys, they're now, don't have the congested flow in their path as much, so they're able to eliminate the head-align blocking. Next slide. Now, if you truly want the lossless environment and we start to back up the congested queue, then we can pause that queue. And at that point, we're blocking the entire class, but the goal is that in that class is effectively only the congested flows. David?
Wanted to quick check on what's going on here. Are you doing dual queues? Are you doing queue pairs within class, or do you need a second priority class to make this work? Right.
So one of our objectives is to try to make this as easy for existing implementations to use. And so the idea is to use an existing traffic class. So we would be using an existing one that's already there. And the reason why is because of that last step. If I'm going to pause the congested queue, I need to actually be able to and use the existing pause mechanism. I need to have an existing class.
Okay, so is that step 4 pausing both queues, or did you put the top queue into what's effectively a separate priority class?
Yeah, it's a good point. It's pausing only that. It would pause initially would pause only that queue. However, there could be some packets still in flight. There's a possibility that we might have to pause both queues. It really depends on what residuals are left in that non-congested queue.
Okay, so I think I've got the answer, which is every time you want to use this for a traffic class, you need to assign another one of the 8 traffic classes to the congestion isolation mechanism.
That is correct. Yeah. Now it would be possible to have, say, 2 or 3 non-congested queues and only have a single congested queue, but you would have to coordinate that. But it doesn't have to always be pairs. But the expectation is that it would be a pair, as you're mentioning. Okay, next slide. So we have some early simulation results. I'm not going to go into great detail. The links are here. But we did see our objective, remember, was to reduce the use of that pause frame because that has been known to cause problems. We did see some reduction of that and improvement in flow completion times, particularly for quote mice frames, if you will. This sort of naturally or statistically does a mice-elephant separation. If you're assuming that the elephants are the guys that are effectively causing congestion, you kind of statistically get that. In a lossy environment, we also saw a significant reduction of packet loss. So by getting the flows that are causing congestion out of the way, we reduce packet loss, and that really has a huge benefit on the mice and control frames. So again, the details are there, and we're going to do some more. There was some questions about the modeling, and as usual, I would love to work with anybody here on simulation if that was an option. Okay, last slide. So what are the next steps? So again, we're socializing this with many people. We need technical review. We'd like to do additional simulations, alternative switch architectures and different congestion control algorithms. I'm very interested how this interplays with things like BBR or other time-based congestion control schemes or rate-based, not explicit marked. And we would hope to progress our motion and start this project in July. So how can the IETF participate? So we already have an IETF IEEE interworking relationship. That would be a great topic for that to discuss. You can email me directly comments, and I'll be happy to work with you, engage and do whatever we can to vet this idea a little bit more. And then we also have, as I mentioned, there was this paper that where we're motivating this problem, and we're talking about the use cases, and would love, again, collaboration on that. It's an open process. Anybody can work on that. We have vendors and we have end users today. So have a read at that as well. And that's it. Thanks. So, any comments?
Matt Mathis. It sounds like this method is focused on there being specific pairs of ports that have hot flows between them.
Well, I showed it when I described it. I'm only showing an upstream and a downstream, but the reality is the cloth fabric, so they're kind of coming from all different directions.
Right. I was going to say, I'm not aware of that many environments where it's a single port pair, and a much more common case is what we call the incast problem, where you have every input port is landing on the same output port, and
correct.
Okay.
Yeah, I use that simple diagram to illustrate the mechanisms. The reality is
because the former problem is probably got a lot less traction as something, but the latter problem, the incast problem,
correct.
It might make sense.
Yeah, if you have a look at our paper, we talk about the key problems, and incast is clearly one of them. Bob?
Hi, Paul. I just wanted to know, most of your presentation is about this is what we're going to do, and then at the end you say, and we want to try different queuing disciplines, different traffic models, all the rest of it. Are you saying you might not do what you've mostly described if someone comes up with something better, or you'll definitely do that, but you might do other things, or what?
Yeah, so the tricky part, as I mentioned in 802 standards, is we're not, it's the balance of how much of it is known versus how much of it is not known, what the answer is. And I mean, we have a pretty good idea on how we want this to work and integrate with what chip models and things that exist today, but it's not done. Typically what we do is put this project authorization request, which defines the scope, and and we've already gone through defining objectives and goals. We can entertain multiple proposals for how to achieve those and bake them off and do all that. That's right. A part of the process. So that's, again, soliciting these ideas.
And might an outcome be that IEEE standardizes a couple of mechanisms, then the sort of market decides between them?
Yeah,
a couple of switch mechanisms, and they can be put in different ways.
Yeah, or we can say, you can say, here's one idea, but it's open to use others. At the end of the day, we want to see this external behavior. We want to see, no packet reordering or some low level, and we want to see a message being sent that gives me enough information for an upstream switch to do, so that's where you have pure interoperability. And then the behavior obviously can't conflict with one another, but try to avoid implementation details if possible. If that makes sense?
Yeah, but what I meant by two, not necessarily two in the same network, but so that one network could use one and another network could use another, but switches have got them both. Do you see what I mean?
Oh,
yeah.
Sure.
Yeah. Right.
Okay. Thank you.
Thank you, Bob. Singamai. Next.
Okay. And this is about the presentation of this the BBR and it's used for L4S with L4S support. And it's a few experiments and findings, and it's quite sort of recent results, and it doesn't claim to be the solutions, and there are other solutions also in the pipe for that others. Okay.
Move the mic.
Not the microphone. Okay. Yeah. Okay. Yeah, and you can take the next slide, please. Yeah. And you probably have seen all this, the BBR, what it stands for and what it is, and it's implemented by Google. And the scope of this work is to modify BBR with L4S support. It doesn't address this, the packet loss issues that are identified with short buffers. And the reason why I want to present is that those changes are very minimalistic, and it's very easy to implement it in real. And these are simulations, that I'm not stress it, that it's no real test beds that are run with this. Oh, okay. Do it like this. Do it my cat felt. Change that for one. And the modifications that are done is that you use L4S support is added, and DCN code is from TCP, and it does this special thing. It doesn't do accurate DCN. And the main change is the functional BBR update bandwidth, and sort of you update the bandwidth computation and remove the number of CE-marked packets in the equation, and divide it by a factor 4 in this case. And it's not 2 or 4, it doesn't really matter that much. And there's some additional state variables, sort of it's a delivered CE needed while delivered is specified, and delivered is the amount of delivered packets, and it's sort of updated to delivered and CE-marked packets. You can take the next slide, please. And the gain cycle is changed from 8 RTTs to 3 RTTs, and also reduce the gain variation a bit. And it's sort of the gain variation is essentially halved. It gives less jitter, but sometimes it can give the slightly slow rate increase. And in some cases, if competing flows in the same bottlenecks, you can get the worse sort of convergence. The mean RTT probing is removed, but that is for simplicity to make it work. And one reason why you can remove is that the L4S gives very short or 0 Q delay. But in the end, you may still need mean RTT probing. For instance, if you have 5G dual connectivity where flows change from LTE to NR, then you can changing RTTs. The bandwidth window is the max bandwidth window is reduced to 2 RTTs or 3 RTTs. And one warning here is that the too short window can actually reduce performance for application limited traffic, and it also gives somewhat more noise in the bandwidth. But the benefit is that you get a quicker rate reduction if you get the congestion. And additional one is that you exit BBR start up if you experience more than 1 RTT of CE-marked packets. That's about it. And you can take next slide. And this is sort of essentially, if you look at, for instance, it's the BBR update bandwidth, it's only the boldface red part is that added in the code. But you need additional code in the TCP input.c and TCP rate to sort of account for the CE-marked delivered packets. But all in all, it's a very simple modifications and gives reasonably good results already. Take the next slide. And here we have sort of a comparison between BBR and this BBR Evo. And it's a simple bottleneck with the minimum RTT 20 milliseconds and an L4S mark threshold of 2 milliseconds. And what you can see is that both track the bandwidth changes marked in red here quite well. And the BBR EV, in some cases, you may not see it here. In some cases, it's slightly slower in the rate increase. And what you can also see that the BBR has this RTT probing that reduces the throughput quite a lot on occasions, which is not present in the L4S adaptive version. And if you look at the queue delay, you can see that the additional L4S mainly reduces the standing queue. It also reduces the delay spike, but that is more attributed to a shorter mean max bandwidth window. So L4S does reduce this the standing queues faster. Okay. And this is an example where I sort of apply a phantom queue, and this is sort of my interpretation of a phantom queue. And in reality, it's done slightly differently with the virtual queues. And you can see that you manage to reduce the queuing delay to almost zero. What you have is actually serialization delay for the packets. And you sacrifice some 10% bandwidth, but you get more noise in the throughput also. Can of course say that this is where throughput is measured over a very short period. It's like 20 milliseconds. So I will actually sort of change it due to RTTs. That. Okay, next slide. And if you look at multiple flows, you can. This is sort of a simulation where you have 5 flows that arrive according to pulse-on arrival process with an intensity of 0.2 flows per second. So they appear at random. First the blue flow appears and then the red, and at some random intervals. And you can see that the BBR doesn't manage initially to sort of keep the queuing delay low, and that's quite natural because you have this latecomers advantage. And that's good, but it stabilizes after a while at least. And the flow rates converge relatively well. Next slide. And if you use this with L4S, then you get a slightly better flow convergence and you reduce the queue delay. But it's not ideal. Ideally, you should have something like 2 millisecond queue delay, but it's more like 5 millisecond peak queue delay. And what you can see also, the newly arrived flows ramp up more slowly. That's because you exit this BBR startup mode. Next slide. And then we have an example with a phantom queue, and you get slightly better convergence, but I can't really say if that is sort of just a happenstance or so. And it's slightly lower queue delay, and that is sort of, you don't reach zero queue delay with phantom queue if you have more flows that are competing with the bottleneck, and that is something that needs to be addressed. Ideally, you should get very even lower queue delays. And then we have next slide. Sort of try to mimic a case where you have, for instance, a beam forming NR, and you sort of get a slightly worse beam forming, and you lose the beam slightly, and the throughput gradually decreases over the course of 400 milliseconds. And you can see that the BBR EVO here managed to keep the queuing delay lower than the BBR. The BBR sort of spikes up to 60 millisecond queue delay. But you don't reach zero queue delay with the BBR EVO either. It's up to like 20 milliseconds. If you look at the next slide, you can see the reason is that the max bandwidth is slightly overestimated. At for 1.05 seconds, you have a too high bandwidth. After that, you get a bunch of CE marked packets, and the bandwidth is pushed down. And then you have this process repeats itself. So more work is needed here to get a better bandwidth estimation. And the trick is here that you can, of course, make this more cautious, but then you can easily end up in a problem that you get worse convergence if you have more flows that compete for the same bottleneck. So it's a choose between the devil and the deep blue sea in some cases. So. A little about RTT fairness. In this case, I must say in this case, it's a very short test, and you can see that BBR EVO is, it expects it behaves as expected, that if you have a longer RTTs, then you get the lower share of the bandwidth. BBR, on the other hand, sort of does it completely opposite. If you have shorter RTTs and compete very flow with a longer RTT, you get the lower share of the bandwidth. It's a feature. BBR EV in this case is sort of makes things, it sort of flip this upside down, or it turns it sort of right side again. And then another example, we have a shorter RTTs and comparison, and it takes the next slide. You have roughly the same behavior, and you can with a shorter RTTs and you have RTT unfairness, differing RTTs, and you get a better RTT fairness with the additional L4S marking. Sorry, that was final. And conclusion of that, it was quite easy to modify BBR for this case. But there are probably better ways to do it with more sort of a brain thing, more thinking involved. And if you additionally add the L4S, you get a quite good convergence with multiple flows competing on the same bottlenecks. It keeps the standing queue small or very small with the phantom queues. And you get a certain degree of jitter, and that is a result of the bandwidth probing that is still present in this with this adaptive BBR. But you need to be in this implementation, need to be a bit aggressive in order to get your fair share of the bottleneck. Otherwise, you will starve. If you're too cautious, then your bandwidth will go away, and throughput will go away. That's about it. So.
We have a few minutes for questions.
Yuchang Chen, thanks for this work. Very appreciative of your the small change about ECN, and it seems very interesting. I would love to try it on our environment too. There is only one change I'm a little bit afraid of, which is to exit a startup or a slow start on the first round of experiencing ECN. I think this will cause the same problem that BB are trying to fix originally, which is on the Google Backbone WAN links, you have this elephant copy flows, and they are getting all this sort of bursty losses or likely bursty ECN signals because of some incast happening, or just bursty small mice traffic driving by. We call that lost by the drive-by traffic. So BBR might be exiting the startup phase, essentially slow start very early, and then we'll have to rely on this either 1.25 gain, or in your case 1.12% gain to slowly grow up to the bandwidth.
It could be right about that, and it could be an issue.
Yeah, so that part we might need to discuss further. Yeah, but I think that the rest looks very interesting. Thank you.
So Gary Fairhurst, I like this piece of work. I like the idea of being able to take some signals and really figure out what to do rather than just carry on blasting into the internet. So this looks really cool. I appreciate this. Your benefits seem to come from multiple things. So one of it was using ECN as a signal at all, which applies to L4S, but would apply to non-L4S. It would apply to ABE or other ECN methods. It would be kind of nice to know if you have a feeling for how much comes from ECN and how much comes from BBR.
Yeah, and I believe mentioned it briefly, and I believe one sort of trick that I did was a shorter bandwidth window, and that was sort of reduces the length of the wave spikes. And the other one is the reducing the standing queue that you could see in the BBR example. One of the early slides where you're changing bandwidths. Yeah. Take some money, I believe the first graph. First graph, I believe. Move for the two slides. Yes. And you can see that the blue graph is sort of the queue delay gradually goes down with BBR. and that is actually that is attributed to the L4S marking, that it cuts the queue delay really fast. But the width of the delay spikes and possibly also the height of delay spikes, that is the chain difference there is due to the shorter bandwidth window.
Okay, I buy this as being a very useful thing on its own, and I like the phantom qubit as well, which is probably something that is a separate thing, but it really helps convergence. So thanks very much for the talk.
Andrew McGregor, Google. I'd like to second Gary's thing about change one thing at a time so that we can see what the impact of each of them is. Now, I mean, as an exploration, this is great work. Don't get me wrong, but from an engineering point of view, it would be very nice to know what the contribution of each of the individual variables is. And I have one to add, which is that one of the things that stands out particularly in this plot is the impact of BBR's max filter window. Consider using something like a percentile tracker and softening it. There's, if you search around, you'll find that there's a way of tracking a given percentile of a distribution, which costs about the same as an EWMA. There'll need to be a little bit of numerical fudging to deal with the fact that the percentile is not actually what you want to track. You want to track an estimate of the maximum, but you know, fudged like that, because that could give BBR a significantly softer response to events in the network and probably eliminate most of those spikes in the bottom graph in the slide. Thank you.
Not sure.
Yuchong Chen. Yeah, I agreed. Right now, the BBR max filter is it's an extremal filter, and I think the main sort of benefit of this ECM work is to actually reduce that effect of max filter, because one problem is everybody's probing, and once in a while everybody get a really good bandwidth and they stay at that. But with this ECN serve as a guidance to say, no, you are way too extreme, because I'm start dinging you, right? You have to reduce your rate, and that's why it would achieve great queuing delay. I do have, and I also agree with Andrew's suggestion. We are looking to use different type of filter for the bandwidth. I have one question here. So I noticed L4S uses sojourn time as a marking threshold, but in most in our data center, we still use instantaneous queue lengths. So what's your thought that if instead of using sojourn time, you use simply like over X kilobytes of queue, I'll mark it? What would the result look like?
I probably need to come back with the answer. So.
Okay, yeah, it would be great to see that. Yeah, thank you.
Exactly.
Neil Cardwell, I also wanted to thank you for this work. I think it's really great to see people experimenting with simple ways to fold in ECN signals to the BBR algorithm or framework. I had a question about, or some comments about the modifications to the algorithm. If it's possible to go back to the slide, that'd be great. If not, that's fine. In looking at the relationship between the gain cycle that's talking about the bandwidth probing schedule and the bandwidth filter window, I would encourage people who are experimenting with variations on BBR to keep in mind some of the design relationships between the time scale in which you probe for bandwidth and the time scale of the bandwidth filter window. And you can take a look at the BBR internet draft. It talks about some of those constraints where you want to basically remember a bandwidth over a time scale that includes some bandwidth probing in order to get robust behavior and not sort of fall over if you see delay variations due to cross traffic or radio bandwidth fluctuations, whatever. And then the second comment would be, I think one thing with the ECN-based BBR, one thing to keep in mind would be that over the lifetime of a BBR connection in the real world, we might have the bottleneck shift from a bottleneck that supports L4S ECN to a bottleneck that doesn't support it. And it would be probably important to think about how these mechanisms could function if the bottleneck shifts in that way so that the behavior is still reasonable. If there's a non-ECN bottleneck that becomes a bottleneck. So for example, the min-RTT probing might need to be always kept there in some form to make sure that the two-way propagation delay estimate maintains anchored to reality. But overall, thank you very much for this work.
Thank you.
Hi, Bob Prisco. I really just wanted to comment on your point about bytes versus time in the queue marking, and it's fine to use bytes if it's a fixed rate link, but if it's got multiple queues and the rate varies depending on the other queues, then you really want to use time. That's this, and there's papers that give you performance results on that. If you want to, I can point you at them.
Different queues, you mean like dual queue? Or dual queue?
Well, our dual queue, or if you've got priority queues, you know, in other words, if the output rate of your particular queue varies depending on the traffic in the other queues, then you can't really set a byte limit because you don't know the rate of your particular queue, and so it's better to do it in time.
Then all the current data center switches are in trouble because they all have multiple priority classes.
Yeah, and this is what these papers show, that you can get a lot better performance if you use time, not.
All right,
It's the same as you know, CODL and Pi and everything. They all use time. Yeah, for that reason. Yeah.
Thanks for the interest. I mean,
All right. Thank you so much, Ingemar. That's good work and a good presentation. Next up, Neil. I'll try something here. Just give me a second. Screw it. I will upload the slides. That's what I'm going to do now here.
Hi, so I'm Neil Cardwell, and I'm going to talk a little bit about recent work that we've been doing on BBR at Google. This is joint work with my colleagues at Google working on the TCP and Quick BBR implementations, including the folks you see here, Van and Yuchang, Ian, Jana, and the rest of the gang. Next slide, please. So I'd like to start with a super quick overview and status of BBR, which most people here are familiar with, probably from previous presentations. And then I'd like to spend most of the time talking about work that our team has been doing on dealing with paths that have large degrees of aggregation, and then close with a few thoughts on packet loss and ongoing work. Next slide, please. So just a quick overview and status. We've talked about BBR at the last couple IETFs, so you're probably familiar with some of these. The BBR is used for TCP and Quick traffic on google.com and YouTube, and internally at Google on the WAN backbone between data centers. This source code is available for Linux TCP and for the Chromium Quick implementation. There's also work going on implementing BBR for FreeBSD TCP at Netflix. We've got a couple internet drafts documenting the algorithm, and then there's some slides and videos from previous talks. Next slide, thanks. So aggregation. So what do I mean here? Basically, there are a number of phenomena where you can get data and/or acknowledgements that are sent in bursts or batches. And generally, when this is intentional, it's been designed for some kind of amortization of overheads to increase efficiency. So this can happen both in shared media, whether it's Wi-Fi, cellular, cable modems, and it can also happen to reduce the per packet overheads using offload mechanisms in order to take a batch of packets on the wire and treat them as a single entity as you pass them down through the stack on transmit or back up through the stack on receive. And so basically you see that on a lot of Ethernet links. And so between all of these links and all of the various techniques they're using, this turns out to be a very widespread phenomenon. So to handle aggregation, BBR sort of decomposes this problem into two separate but related problems. The first is, how do you bound your sending rate based on the estimated rate at which your packets are making it through the network, basically your bandwidth estimate. And one of the two drafts we have out talks about that approach that we have been using so far for delivery rate estimation, and there are links there. And there's ongoing work on improving that. Basically, a couple different approaches we're looking at, but both have the flavor of looking at bandwidth over longer time scales. And then the second part of the problem is, once you have a bandwidth estimate, how do you use that to sensibly bound the amount of in-flight data in the network, which is to say, how do you set your C-wind? And as a first approximation, the initial release of BBR basically has a sort of simple approach where it generally bounds the C-wind to twice the estimated bandwidth delay product. So twice the bandwidth times the min RTT. Of course, this can run into challenges if your RTT is noisy. So here's an example. Next slide, please. So this is a trace from a case where there's a Wi-Fi bottleneck. So it's just a sender, one Ethernet hop, Wi-Fi access point, Wi-Fi network, laptop receiver. And here, this is 5 seconds of traces showing every RTT sample that we get. And it's a bit small, I guess, but you can see that the RTT sort of bounces all over the place from 4 milliseconds at the bottom all the way up to roughly 80 milliseconds. So the RTTs can be kind of noisy here. So this is one of the challenges, and we can sort of drill down and get a sense of what's going on if we take traces at both ends. So next slide, please. So I wanted to spend a little time doing a deep dive on one particular trace, just to illustrate some of the issues that you run into and how they impact the approach we took for dealing with this. So here's a single trace we're going to be looking at, and this is just a very simple TCP transfer of 20 megabytes. This is a Linux TCP BBR sender going over the public internet to a cable modem in a typical Wi-Fi home network and a laptop receiver. And we took some traces on the sender and the receiver with TCP DEM. Next slide, please. So if we look at things from the perspective of the receiver, it looks kind of reasonable. The data is mostly arriving kind of smoothly. This is a time sequence plot. X-axis is 2 seconds of worth of time. Y-axis is 20 megabytes worth of data. You can see the data arrives fairly smoothly, and then the TCP sender is enqueuing the ACKs smoothly. There are a couple flat spots that are kind of interesting. Then those turn out to be from when the sender is C-wind limited or receiver window limited, which we can see on the next slide. Next slide, please. So this is the same trace, but from the perspective of the receiver, and this one's a little more interesting. You can see that basically the sender is largely sending pretty smoothly, but then there will be long periods where the ACK stream just sort of disappears for a while and the ACKs go silent. And in those cases, the sender sends for a little while at its estimated bandwidth, but then it runs into its C-wind bound of twice the bandwidth delay product, as I was saying. And then eventually, after a while, there'll be a big burst of ACKs that arrives, the sort of vertical blue segments here a little while later. And we can zoom into the circle here on the top right, and the next slide. Next slide, please. And this is what it looks like from the sender's perspective, zoomed in. So we're sending along in this green transmit line at our estimated bandwidth, and then all of a sudden the ACKs disappear, and we get a flat segment in the horizontal segment in the blue line. And there's sort of silence in the ACK stream. And eventually we get a big aggregated ACK, the bunch of data acknowledged in a single burst, which allows us to continue sending. And it's this is kind of the phenomenon that we see over and over when there's aggregation. Next slide, please. If we look at that same moment from the perspective of the receiver, it's a little bit interesting. The big aggregation effects that are visible to the sender, in this case, are not showing up at all on the receiver. from the receiver's perspective, what happened was during that time here where the lines are smooth and diagonal, the data arrival is smooth, and the receiver is enqueuing TCP ACKs on its own receiving host smoothly. But basically, as we could see from the previous trace, actually those ACKs apparently are not making it out on the network. And so, there are a number of phenomena that could be happening here, but it appears that basically the Wi-Fi access points data transmissions are monopolizing the link for a while. And the result of this is that since the ACKs are not making it out on the wire, the sender, as we saw on the previous slide, runs out of C-wind, goes silent, and that gives us this flat horizontal section following there, where the link is underutilized because the sender stopped sending. Next slide, please. So how can we deal with this? So at a high level, BBR is sort of aiming to keep the minimum amount of data in flight that's required to achieve the available bandwidth that it sees. And in the first rev of BBR at a high level, the C-wind is generally bounded to twice the BDP. And that's because basically there's one BDP that's budgeted for utilizing the pipe, and then one BDP that's sort of budgeted for a delay variation that you can see in the path. And that's sufficient for full utilization if and only if the delay variation is less than or equal to the min RTT. But as we were just seeing in previous slides, obviously delay variation can be quite high. So what happens is if the delay variation is high, then as we saw, the sender exhausts its C-wind and underutilizes the link. And the lower the min RTT is, the more likely you are to run into this situation. Let's see, we lost our, okay, I can, thank you. So, and in fact, this can happen even on the public internet, because often content distribution networks will try to place their sending hosts close to the user for a good user experience. So the min RTT might be just 1 to 20 milliseconds, whereas as we just saw, the Wi-Fi delay variation can be quite a bit higher, up to say 80 milliseconds. Next slide. So to deal with this, in the past half year or so, the BBR team has implemented an explicit aggregation estimator that is basically asking how much excess data can be acknowledged as a sort of aggregate over the time scale of a single flight of data or a single C-wind. And it does this by sort of estimating the windowed maximum degree of aggregation that it's seen recently, and then uses that estimate to provision or allow itself, if needed, extra in-flight data so that it can keep sending during these long silences in the ACK stream. And it does this by basically saying, what's the extra amount of data that we saw acknowledged over some time window beyond the expected amount? So specifically, we can calculate the extra amount of ACKed data as the actual amount that was ACKed minus what we expected. And what we expect is sort of the estimated bandwidth times that sampling interval. And then we can take the maximum we've seen over some recent time window and add that into our C-wind that we allow ourselves. And there's of course a question of how recent is recent. And here we basically tried to keep that window at roughly the same time scale as the estimated bandwidth filter. And then as a sort of safety mechanism, sort of bounded that extra ACKed amount by the C-wind. Since of course over the time scale of a single flight, you shouldn't have more delivered than your C-wind, obviously. Next slide, please. So here's just a quick way to visualize the mechanism here. The idea basically is that when we're sampling the extra amount that's been acknowledged, we take the actual amount that's been acknowledged, just sort of the entire blue height here, and then we subtract the amount that we expected to have acknowledged, which is the green vertical segment here, and we computed that from the estimated bandwidth times that sampling interval on the bottom there. And that gives us the, if we subtract those two, we get the extra amount that was ACKed, which is the red part here. And that's the part that we allow as extra C-wind, essentially. So next slide, please. So this there's code for this that's already been deployed for the quick Chromium implementation of BBR, and you can click through the link there to see that. And then there's also a TCP implementation that's being rolled out on google.com and YouTube for some global experiments. And then here are just some quick examples in a controlled environment where you can see the kind of levels of improvements, sort of in this particular network, for example, in a Wi-Fi network, when using 2.4 gigahertz, there's sort of a 4x increase in throughput, and then in 5 gigahertz, there's sort of a 10x increase in throughput. So some significant improvements. Next slide, please. So in addition to the work on explicitly estimating the degree of aggregation in the path, a second mechanism that we've been working on recently is a mechanism to adaptively drain data from the network to maintain shorter queues on a more regular and basis. So in BBR, in the steady state, there's this basic approach that we call gain cycling, where you, in general, pace at some pacing gain times the current estimated bandwidth. And you spend a little bit of time probing for bandwidth by sending with a pacing gain above 1, a little bit of time draining the extra data in flight from the network by pacing at lower than the estimated bandwidth, and then holding steady for a while, sending out exactly the estimated bandwidth. And in the initial release of BBR, the drain phase was held generally for about 1 times the min RTT, or the two-way propagation delay estimate. And that can run into issues where if there are variations in the available bandwidth, then that can end up pacing out more data until we reach the C-wind, and so there ends up being twice the estimated BDP in flight. So the new mechanism that we've been experimenting with, we could call drain to target, which basically, instead of holding the drain phase for only 1 min RTT, it sort of adaptively holds that state until the in-flight drifts down to the estimated bandwidth delay product in order to try harder to adaptively drain more of the excess packets out of the network. So in various rounds of experiments, we've sort of found that you need to be careful how you do this. There seem to be a couple ingredients to making this work well. You sort of need to bound the amount of time that you spend draining the data, because if you spend too long, then you can run out of good bandwidth estimates in your filter. So you need to make sure that you do probe for bandwidth within the time scale of your bandwidth estimating filter. And then we also noticed that you seem to need to randomize the phases of the gain cycling in this kind of approach to avoid always having the elephants and mice probing and draining in sync. And then we found that it was, practically speaking, it was necessary to deploy this in tandem with the aforementioned aggregation estimator, so that if you're trying to robustly drain data out of the network, excess data out of the network, you do need to sort of allow yourself to put more data in if the ACK stream dries up and the ACKs disappear for a while. So anyway, so we've been doing small-scale experiments with this on YouTube and seeing nice reductions in RTT and packet loss, and we're in the process of doing a global experiment next. Next slide, please. So there's also work on BBR going on outside the Google teams. As I mentioned, there's work going on at Netflix. There's also, there was recently an implementation of BBR for NS3 that was released there with a little tech report accompanying it. The links are here. The BBR is also one of the many interesting congestion control algorithms that the Stanford team is testing in their really neat system called Pantheon. I encourage you to check that out. Next slide, please. And then I wanted to share a few quick musings on packet loss.
Before you go on, Neil,
yeah.
Did you have a clarification question, Richard, or do you want to?
Yes, it's actually a clarification question.
Oh, okay, sure.
About the ACK aggregation thingy.
Yeah.
You mentioned that it is bounded by a C-win. Is that including the receiver window in that state? Because it's not explicitly mentioned. It's two slides earlier, I believe.
results. Yeah, or the next one before that.
Yeah, so right now it's not explicitly bounding itself by the receiver window when it's doing that filter. We could certainly do that as well. We could say, okay, this should not be bigger than the C wind and it should not be bigger than the R wind. Is that what you're suggesting?
So if you have this aggregation phase, obviously the X do not come back to the sender, right? So in theory you could exceed the receive window that the sender knows at that point in time, right?
Yeah, well, obeying the receive window is sort of, I think, a sort of a separate or orthogonal issue. Obviously, we never ignore the receiver window.
So it's implicit. So you implicitly honor this at all states.
Yeah. So
Okay.
there are separate mechanisms in Linux or Quick, I assume, that make sure they never disobey the receive window. Yeah. So from my perspective, with packet loss as a signal, the question is not really whether to use packet loss as an input signal. Obviously, Reno and Cubic use packet loss as a signal, and even all of the versions of BBR that we've experimented with also use packet loss as an explicit signal. I think the key question is really, how can we use packet loss effectively as a signal to adapt the transport sender's behavior? And I think there are some really interesting fundamental issues here. Because where packet loss results from congestion, there's still the question of time scale. So to take two examples, for example, if the buffer is only 1% of the bandwidth delay product, then you can have situations where a link can be 99% idle, even if you've got over the time scale of a round trip with packet losses. Because there can be a burst that can fill that tiny little queue, take some losses, and then people back off, say, and then leave the link idle for the rest of the round trip. And then at the other end of the spectrum, you could have a buffer that's nice and big, say it's 100% of the BDP, and you can still have, if you look over a slightly longer time scale of, say, 10 round trips, that link might be fully utilized for the first round trip, but then completely idle for the next 9 round trips. And so I think, given these kinds of issues, I think part of the key question is, on what time scale should a congestion control algorithm reprobe for bandwidth once it's seen a loss signal? And there's sort of an interesting tension between minimizing packet loss on the one hand and maximizing application performance on the other hand. Now, obviously, most of the time, reducing queuing and packet loss generally reduces the application latency, but up to a point. But if you try to absolutely minimize queuing and packet loss, it doesn't always mean you've maximized application performance. So to absolutely minimize queuing and packet loss, you essentially need to send quite slowly and probe for bandwidth slowly and rarely. And that can cut your loss, but it can also mean that you're not well utilizing the network and can thus increase your app latency. And it's kind of an interesting trade-off. And we've actually seen this repeatedly as we look at tuning congestion control algorithms in data center workloads. We've seen it with several different congestion control algorithms, not just BBR. Anyway, so those are just random musings. Next slide, please. So in conclusion, we've talked about the status of the first version of BBR, and we're actively working on improving it. We know we've got some work left to do. There's work going on in several places, and right now, at least at Google, the focuses are sort of how to deal with aggregation, how to deal with the packet loss signal. I talked in November about one iteration on the BBR response to packet loss. And then we're also working on the dynamics of sharing with loss-based congestion control and AQMs. And there's, as I said, work going on BBR at Netflix as well. And of course, we're always happy to hear ideas, see patches or test or experiment results, look at packet traces, all that sort of thing. Next slide, please. Yeah, so that's all I have. And like to thank these folks, and there's a link if you want more info, and we're happy to take questions and comments.
Yeah, Toki Harlan Jarensen. For the Wi-Fi tests, all the examples you show had the TCP sender, at least one Ethernet hub, away from the Wi-Fi link. Have you run experiments where the BBR sender is the same machine that has the Wi-Fi device in it?
We have run results. We have run tests with that, but I don't have any traces or numbers for you on that.
Does it help for that as well? Like,
sorry?
Your order of magnitude improvement, does that come in those cases as well? Because
That's
we've seen some like what I've seen is this phenomenon where because you don't have enough Q in the Wi-Fi device, you get less aggregation because there's not enough data to build the aggregates.
Right.
And BBR was especially bad for BBR. So I was wondering if you've looked.
Right. No, that's a great question. We I think we'll have to go back to the we'll have to run those tests as well and see how much it helps for that case as well. I think it will help to some extent. I think the open question would be how much is left on the table after this patch. But thank you. That's a great point. Thank you.
Matt Mathis, I wanted to add a couple of footnotes about some other things. The issue about aggregation is actually a really critical problem in this community. And the issue is, I believe it to be true that the majority of humans on this planet are behind links that exhibit these kinds of behaviors. And the constraint is that if you have ACK aggregation going on, you don't have a way of precisely controlling delay. You just don't have enough information. And this is a fundamental problem here, that in places where you have full duplex wireline connections, it's easy to imagine precisely regulating queues. And that is not the case in wireless, and not the case in most of the southern hemisphere, and not the case in lots of places. And so we're looking at a divided problem space, probably. And the other thing is, I've become very concerned recently, the ruminations about loss. All of the plots we've been seeing here have been what I would call bulk flows, not transactional workflows. And I think there's a lot of stuff there that we haven't even begun to look at.
Thank you.
Marie-Josée Montpetit, I'm the chair of the coding group, research group, and it's with my chair hat that I'm talking here. Actually, in our group, we started investigating how to deal with loss by using some form of loss coding, especially inside Quick, and also how this interacts with congestion control in particular. So I think we're interested, but I think there could be also some collaboration that could be possible.
Okay, thank you very much. If you could email us, that would be great.
I will.
Thank you.
Hello, Kevin Smith, Vodafone. I've got two quick questions. So first of all, on, for example, the Vodafone UK 4G network today, would Google services be using BBR?
Yes.
They would, thank you. Okay, and the second question is regarding loss and how you deal with loss. This is maybe an open problem, which is, are you attempting to use a way to distinguish between loss versus the fact that the radio layer may well be retransmitting at the physical layer 1, layer 2, layer 2.5, for example?
Right. No, we're not attempting to distinguish those in BBR. But what I would say is that typically what we see in traces of cellular traffic and Wi-Fi traffic, and our team, everybody on our team has spent a lot of time looking at the traces. Typically what we see is that the link layers in cellular and Wi-Fi networks tend to do a very good job of link layer retransmissions that completely fill in most of the holes most of the time.
Yeah.
So in our experience looking at the traces from TCP's perspective, what we see is high delay variations like the traces that we saw here. And we don't see those manifest as packet losses at the TCP layer.
Sure. No, thank you. I'll be interested in exploring that further with you. So cheers.
Great. Thank you.
Thank you.
I'm inserting myself in the queue after Andrew.
Andrew McGregor. I noticed there was periodicity in the flat spots in your Wi-Fi trace, and the periodicity was 102.4 milliseconds. So what was happening was something attached to that access point was in power save mode. And what you were seeing was the time it took the access point to drain its power save queues after a beacon.
Okay. What sort of device do you think might be in power saving mode in this case?
I don't know. Could be
Okay.
anything. It could even be your BBR endpoint having part of its traffic power saved, which is not supposed to happen, but does.
Okay. Yeah, because in the receiver side traces, it seems like it's pretty smooth. Yeah. Okay. Yeah. Maybe we can talk offline.
So that
about
can
it.
happen. The other observation is maybe packet loss. You need to think about the situation that shallow buffer packet loss is generally pretty much Poisson distributed, random drops. But other causes of packet loss will have strings of correlated losses. And maybe we need to treat 2 and 3 consecutive drops as different from one, as a heuristic toward looking at the whole distribution and time of the packet losses, which tells us about the cause of it, and if it's buffer loss, the integral of the tail of the distribution of rates going above what the buffers can sustain.
Yeah, I agree that there's probably some signal in there that can be looked at
It might
in
be
order
hard.
to differentiate. Yeah, it might be really hard, and so I think that's probably going to be a long-term, ongoing research effort. And the question would be, what's the simplest mechanism that you can deploy that will behave reasonably, even if you may not have a complicated mechanism to distinguish different kinds of packet loss. But yeah, I agree that that's an interesting research area.
Jana Angar participating from the floor. I just wanted to make a general comment, and this is entirely my. Anyways, I want to make a general comment about loss rate. I don't like the word loss because it's really retransmissions that we're counting here, not losses. But beyond that, I think there's something important. I think there's something important in that nuance, which is that sending additional retransmissions. I think your slide on the meditations on packet losses is spot on. There's a very clear tension here between application performance and most pertinently right now for me, and I think for most work that folks are doing in transport now, it's latency. And there's a tension between latency as observed by the application and retransmissions that a sender is willing and able to do more aggressively. Increasing retransmissions, in my opinion, should be completely reasonable, and it should be a reasonable thing that we're willing to give to gain some latency back, or to reduce some latency, I suppose. And in that spirit, I want to encourage folks to think about the mechanisms and the work that's happening here as not to try and reduce the retransmission rates all the way back down to what we know and are used to in Reno or Cubic, but to something that's reasonable. It doesn't have to be the same as what Cubic or Reno has, and that should be perfectly fine as long as it's not 50%. Obviously, at that point, the trade-off it's not a trade-off anymore at that point, or you've gone way past the line. But I think it's completely reasonable to increase the retransmit rates significantly from where they are right now for Reno or Cubic in order to get back some of that latency.
Thank you.
Nice.
All right. Thank you very much.
Thank you, Neil. It's Michael next. Let's see now. Let's get this. Is that maybe? All right. Go for it, Michael.
Great. Hi, everyone. Thanks a lot for coming, and thank you, Jana, for the invitation. So I want to talk about...
You're going to have to speak into the mic.
Oh, sorry. Can you hear me now? Okay. I want to talk about PCC, or Performance-Oriented Congestion Control. Next slide, please. And PCC is a collaboration between my research group at Hebrew University and Brighton Godfrey's research group at Urbana-Champaign. And everything I'm about to tell you is based on 2 publications, one from 2015 at USNIC NSDI, and another that's upcoming also at NSDI. Next slide, please. And PCC is currently being evaluated in various places, and hopefully soon more will follow. Next slide, please. So before diving into PCC, I want to say a few words about what TCP we think does wrong. So think of a scenario where you have a flow, you have a connection F sending at a specific rate R, right? And and there's packet loss, right? So there's many reasons why this might have happened, and there's many things you can do in response. Enter, please. Yeah. So you experience packet loss. What's going on in the network? So one option is that you're the flow causing congestion. That is, you're a big flow, you're bombarding a bottleneck link somewhere, and for that reason, there's congestion. In which case, you should decrease your rate by a lot, even for selfish reasons, right? A different option is that you've just exceeded some shallow buffer somewhere, in which case, you should decrease your rate by just a little bit. Now, yet another option is that you're an insignificant flow, there's some other flow that's big and that's causing congestion, right? In which case I would argue you need to maintain your rate, right? Certainly you don't need to decrease it by a lot. And the last option, which this is not an exhaustive list, but the last option here is think of non-congestion loss, right? Due to physical layer corruption, due to the medium, due to handover in mobile networks, whatever, right? If you get loss that's random, then you're alone on a link and 1 out of every 200 packets is dropped. I would argue that you need to fully utilize that link, right? So in that case, you actually need to increase your transmission rate until you actually do start to suffer congestion losses. So yeah, next slide, please. So the key point here is that TCP's design philosophy is such that you hardwire a mapping from packet level events. That is, a packet was dropped, I received an ACK, the RTT of a packet was more than some bound, to changes in the congestion window. And no such hardwired mapping can be optimal across all of these scenarios, right? So stepping back from this, the abstract question is, what's the right rate to send at? Right? And the key observation is that it's really hard to figure out what's going on within the network, but regardless of what's going on within the network, there's something you can quantify. That is, if you send at a specific rate, you can quantify the outcome in terms of the implications for performance. And you can formulate that. So yeah. So specifically what PCC does is it tries out different rates. So you pace yourself. You send at a specific rate. You wait long enough, think RTT or slightly over an RTT, for ACKs to return, for selective ACKs to return. And you gather statistics, meaningful statistics that pertain to performance, like what's the loss rate, what's the throughput, how fast is latency increasing during this monitor interval, et cetera, et cetera. And then you derive from these statistics a utility value. So you aggregate these statistics using some utility function into a numerical real value that intuitively represents the score in terms of performance. That is, how happy am I with what just happened, right? So for now, think of a very simple utility function that's just the throughput times 1 minus the loss rate. Okay, so that's maybe the most basic utility function one can employ in this case. It ignores latency and it's pretty straightforward. So what PCC basically does is it divides time into consecutive intervals. And each such monitor interval is devoted to trying out a specific rate. So you can think of this as a sequence of micro experiments. We test different rates one after the other. And so at first we send at a rate of R1, we collect statistics, we aggregate these statistics into a utility value U1, then we send at a different rate, R2, we do the same thing, and now we have a different utility value U2. And the crucial point is, how do we determine what the next rate should be. So there should be some online learning algorithm that determines, based on our previous interactions with the network, based on the different rates we tried, based on the different statistics we collected, based on the different utility values, what should happen next. So at a very high level, this is the PCC architecture. So you learn real performance in the sense that you choose a rate, you gather statistics, and you provide a score that indicates the performance level. You control based on this empirical evidence, and this we're going to show yields consistently high performance. And going back to TCP, there's two crucial aspects here. So one is that, thank you, that we gather meaningful statistics, right? So the fact that a packet was lost doesn't tell us much. The fact that the loss rate is 0.5% does actually mean something. The second thing is that we apply an online learning algorithm to adapt our rates. So I'll talk about what that means in a few slides. Yeah, can you still hear me? Cool. So so the first version of PCC, presented in 2015, called PCC Allegro, employed a fairly simple rate adjustment algorithm. So there's a lot of details, but I want to give the high-level picture. So think of sending at a specific rate R and deriving a utility value of U, right? So now you need to decide whether to go up or down, right? So you're in this decision-making mode. And the question from PCC's perspective is, will I gain higher utility if I go up? Will I get better performance, or will I get better performance if I go down? Right? So the way PCC v1 handles this is it does random control trials. Right? It probes a higher rate, it probes a lower rate, and based on empirical evidence, it decides in which direction to move. So in this case, for example, say that you are sending at a rate of R, you try a higher rate of R times 1 plus epsilon, the lower rate of R times 1 minus epsilon. Let's say you do 2 experiments, right? So you send twice at the higher rate and send twice at the lower rate. And in this case, as you can tell in the figure, the results are pretty conclusive. It didn't have to be this way. But in this case, it's pretty obvious that I gain higher utility when I send at a higher rate, and so I will move up. Now, obviously, there's a lot of details I'm omitting because, firstly, I wouldn't want to go into this decision-making mode each and every time, right? So PCC doesn't do that. PCC basically enters a decision-making mode when there's evidence that the direction is no longer the right one. And I'm not going into the details about how we choose this exact step size, which is also adaptive, right? But this is the high-level picture. The high-level picture is gain empirical evidence, right? And move in the empirically maximizing direction, which translates in PCC to the utility maximizing direction. So one thing I want to point out is that even this fairly straightforward scheme is enough to distinguish between some of the cases, and actually all of the cases we've seen before. So think of the scenario where I am a large flow causing congestion, and the opposite scenario where there's random loss, right? So 1 out of every 200 packets is dropped in expectation regardless of what I do, right? So in this case, utility behaves very differently, right? If I'm sending at a certain rate in the first scenario and I increase my rate, then because I'm the flow causing congestion, loss rate is going to go up, right? I'm the problem. In the second scenario, if I increase my rate, the loss rate is the same, right? Because it has nothing to do with me. And this is translated to different choices of rates because the utility maximizing direction in the first scenario is going to be decreasing your rate. Whereas in the second scenario, it's going to be to increase my rate because I'm getting more good put and my loss rate doesn't change. So one important thing to note is that congestion control here is handled differently than in TCP. So the question is, where's the congestion control? So in TCP, congestion control is exogenous to the protocol, right? That is, we hardwire into TCP behavior that says, if you experience packet loss, interpret that as congestion. And once you interpret that as congestion, react in a certain way. So PCC doesn't do that. And thank you. So in PCC, again, please. Yeah, so in PCC, we have different senders, each employing an algorithm that maximizes its own utility. And the crucial point, I think, is that selfish doesn't mean aggressive. If my utility function is such that I don't want, right, that I suffer from excessive loss, right, then so will my behavior. So my behavior will be consistent with that. So we think of this interaction between flows as inducing a non-cooperative game. We have different senders. They optimize their own utility functions. But if the utility functions are such that the resulting equilibria are good, for example, where the loss rate doesn't exceed a certain bound, then that's what we're going to converge to. So a lot of the engineering is devoted to figuring out what the right utility functions are. Right? So which utility functions induce good equilibria? So in PCC v1, this was handled in a certain way. So going back to the utility function, the simple utility function I mentioned before, where it's basically just the throughput minus some penalty for loss, right? These utility functions aren't actually going to behave that well. But when you plug in another factor, and you can look at the paper for the formal analysis, right? Another factor that penalizes loss further, that what you actually get is a unique equilibrium that you're bound to converge to that's fair and where the loss rate is bounded. Sorry. Yeah. So here are some experimental results. So what you see here is a side-by-side comparison of PCC and TCP cubic so we're sending on a single link, and flows come and go. So first we have, the x-axis is time, the y-axis is throughput, the red flow enters and it's alone in the beginning, then the green flow enters and so on and so forth, and then they start leaving. Right? So what you see in the bottom figure is that PCC basically converges to a stable equilibrium where each of the flows gets its fair share and stays there until the situation changes. That is, until another flow is added or one of the flows is removed. So here's another experimental result, another depiction of experimental results from the paper. There's often a trade-off between convergence rate and how variable your rate is upon convergence. So often you'd have things that converge fast where you see high standard deviation once you converge, are the opposite, right? Where probing is slow, but then you might stay at a fixed point. So what you see here are different protocols and where they're located in terms of convergence time and the standard deviation of the throughput upon convergence, the y-axis. And below, at the bottom, you see different points corresponding to different choices of parameters for PCC. So what you can see here is that for quite a few choices of parameters, you actually get better trade-offs than most existing algorithms out there. So here's one more result I wanted to show. So this is an attempt at quantifying reactivity to rapidly changing network conditions. So you have an emulated environment where every 5 seconds, the network parameters change drastically. So the bandwidth changes, the RTT changes, and the loss rate changes. And what you see, the blue line is the optimum sending rate in hindsight. This is what you should have done had you known, right, that these would be the exact network parameters. So what you see is that cubic performs really badly on this example. It's because it doesn't contend with loss well. TCP Illinois performs somewhat better, and PCC Allegro is actually very close to the blue line, right? So it pretty much is able to track the optimum in this example, and I'll actually revisit this example later when we talk about PCC v2, because there are some subtleties involved here. Okay, so we've run a lot of experiments in the course of the last 3-4 years, and all of these are documented in the paper. So please take a look, and I'd be happy to could you go back one slide? Thanks. Are documented in the paper. We've run experiments in many different emulated scenarios and also in the wild. And one thing I want to note is we've run experiments in the context of inter-data center, intra-data center, satellite networks, et cetera. And what we see is that we get significant performance benefits in each of these scenarios. But one important thing to note is that this is the same PCC implementation, but each and every time we're comparing against the TCP variant designed specifically for that environment. So this is the same black box PCC implementation. Okay. So here's a graphic portrayal of some of the experiments we've conducted. These are 510 source target pairs. So each and every line represents a comparison of PCC and TCP cubic between the associated points. And the color index is how much higher is the throughput, right? So in the median, it's 5x. Yeah. Okay, and this is my favorite figure from the NSDI 15 publication. So this is sending a lot of data over a very long path. So this is sending 100 gigabyte of data over very long paths. You see from Utah to Berlin, from Utah to China, from Illinois to Waseda. So the green represents TCP cubic, and the yellow is taking a flight, right? Basically, and PCC is the blue. Yeah, this is the internet in the 21st century. So there's there's a lot of work for this work group. So a few words about deployment and deployability. So there's one interesting observation, which is that TCP is a really bad learner from an online learning perspective because of this hardwired mapping. So for example, it doesn't do one of the most basic things that you'll find in any online learning algorithm, which is trying to close the feedback loop with the environment. So this is what I mean by saying that when I go up, does the loss rate go up? Does the latency go up? Or do they stay the same? This seems to be crucial for dictating what I do next, right? But in TCP, because you're reacting to a packet level event, right, that information is not available to you. So, but the more important observation from a deployability perspective is that the TCP sender might be the bad learner, but the TCP receiver is really trying to help it, right? So when you think of the TCP receiver, it's actually throwing a lot of statistics at you, right? Which you could theoretically utilize. And from a deployment perspective, what that means is that PCC doesn't actually need to change PCC doesn't actually need to change the TCP receiver. So the receiver can still run legacy TCP. You don't need to change the application. All you need to do is change the part of TCP in the kernel that adapts transmission rates. So that's the part you need to change. This can be implemented as a kernel module. And this is basically what we did. So this is the high-level software architecture, but I think that's the main point. The main point is that all you need to do is generate a kernel module that just changes the algorithm TCP employs to adapt rates. So this was in 2015, and since then we've continued working on PCC quite a bit. And the reason is that PCC Allegro is still far from optimal. And the more challenging the environment is, or the more challenging the applications are, the worse it performs. So in particular, it suffers from some suboptimal convergence rate. We did incorporate to some extent latency into PCC v1's utility function, but it wasn't done in a very principled way, and we actually did very little experimentation. There was no formal analysis of this. It suffers from bad performance in mobile networks, and for LTE, for example, I'll revisit that. And also from suboptimal quality of experience in the context of video streaming. I'll revisit this point as well. So in an upcoming publication, we're presenting PCC Vivace, which we've already experimented with and is being evaluated in several places. And thanks. Yeah, and PCC Vivace is another embodiment of the same high-level architecture, but there's two fundamental changes that pertain specifically to the utility function framework and to the algorithm, the online learning algorithm that we employ to adjust transmission rates. Right? So, yeah, thanks. So we're changing the utility framework and we're changing the online learning algorithm. Cool. Next slide, please. So without diving into the details, and soon the paper is going to be available online, and the code also. A few words about what we did. So the new utility function framework incorporates latency explicitly, and this required changing the original utility function of PCC v1 quite a bit, and is intended to provably provide better convergence. That is, both faster and more stable. Another thing, which is a pretty crucial feature of PCC v2, is that different senders can employ different utility functions within the same broad class of utility functions without compromising convergence. Right? So we can tweak the utility functions of different senders to accommodate their different performance needs. Right? Some might care more about latency, some might care more about bandwidth, right? While still guaranteeing that they converge to a stable state, and while also enabling us to reason about what this stable state might look like. Another thing that changed is the simple online learning algorithm that I described before, where basically you had random control trials and you were probing in both directions, trying to figure out what the right direction is. So again, there's a lot of details. Some pertain to how do we handle noise, right? That is how we are gathering statistics, but these statistics might not be accurate. Think of a scenario where I'm sending at a low rate. If I send just a few packets, it's really hard to get accurate statistics, right? And there's other scenarios where this might happen. So this is one thing we needed to address. There's also various issues related to the step size. But one thing I do want to mention is in PCC v2, called PCC Vivace, we don't just use the utility function to determine what the right direction is. We also use it to determine by how much we should change the rate, right? And this is done by looking at the gradient of the utility function, right? That is, if I increase my rate, if at this point in time, the gradient looks like this, right? I should increase my rate by quite a lot, right? As opposed to maybe I'm very close to a stable state and I should just probe a little, right? And go up by a little bit, right? So this online learning algorithm is intuitively based on doing gradient ascent on the utility function. And there's a lot of results in online learning theory that show that not only does this result in performance gains for the individual sender, but also if different senders interact and they play well with one another. So it's interesting to contrast PCC with BBR because these two reflect very different design philosophies, right? BBR tries to track the bottleneck bandwidth, and TCP and PCC employs online learning and try to learn from empirical evidence. But they're also somewhat similar because both rely on pacing and both rely on going beyond packet level statistics and trying to gather statistics at longer timescales. So one thing I want to mention before we go onwards is we have compared against BBR v1, and I know that the BBR team has been working on various improvements, and once BBR v2 is available, we'd be thrilled to play with it. Yeah. So going back to the figure we saw before, where we tried to quantify how reactive different protocols are to changes in network conditions. So again, we have a single link, right? And the network parameters change every 5 seconds. And what you see here as the dashed black line is the optimum sending rate, right? This is what you should have done in hindsight. So notice that both PCCs, that is both PCC Allegro, the old version, and PCC Vivace, the new version, track that line pretty well, but also notice that PCC Allegro, the old version, often overshoots, right? And when it overshoots, that results in excess latency, right? Because it's sending above the rate and packets get queued, et cetera, et cetera. PCC Vivace does much better because most of the time, the vast majority of time, it's close to the optimum, but it's beneath the dashed black line. BBR has somewhat bizarre behavior here. As you can see, it sometimes dips and takes a while to recover. I conjecture that this is associated with scenarios where the behavior of this network deviates from the network model that underlies BBR, but it'd be very interesting to see how BBR v2 does in this context. Yeah. So one important thing to notice.
Is it possible just to ask on the previous slide what you were showing? Go first. Are these each individual runs against exactly the same channel model?
Yes.
Right,
yes.
okay.
So this is an emulated environment.
Yeah.
Every 5 seconds, all the parameters change, and they change by choosing a uniformly at random a parameter within the specified ranges, right? And then you basically just run these protocols against exactly this. Oh, sorry about this.
I got it though.
Okay. Wonderful. But yeah, but just to repeat my answer. So this is an emulated environment. Every 5 seconds, we choose parameters uniformly at random from these ranges, and we run all of these protocols against the exact same choices of parameters. Sorry? One at a time, right. So one thing I want to mention is that the way you react to changing network conditions has implications for quality of experience. So here's an experiment that's basically doing the same thing, only now we're measuring quality of experience for streaming video, right? And we're measuring that in terms of the buffering ratio, which is the time you spend buffering at the client out of the total time, right? So ideally, the buffering ratio will be 0, right? Lower is better. So what you see on the x-axis are different bit rates, the 4 standard bit rates, and the y-axis is the buffering ratio. So the upper line is TCP cubic. As you can see, BBR does significantly better, and PCC Vivace is actually quite close to the bottom in this example. And once again, these are emulated network conditions, but we actually also run this experiment. You can see that in the paper on streaming video from AWS to residential Wi-Fi. Right, so there are such experiments as well. But if you, next slide, please. Another interesting phenomenon is that as the number of complete, so the previous slide was for one flow, but as the number of competing flows of video streams increases, the gaps actually become bigger. And the reason is that stability and convergence play a role, right? You want the flows to play well with each other. So this is what you see here. So the BBR line goes somewhat higher, and the PCC line is still pretty much close to the bottom. Yeah, so here's another set of experiments. This time, we used Mahi, the network simulator, to replay Verizon LTE traces. And what you see here is different points on the trade-off between self-inflicted latency and throughput. So it's very easy to do well in one of these individually, right? If I just blast away, I'll get perfect throughput, but I'll generate a lot of latency for myself, right? Because packets will be buffered. On the other hand, if I send one packet each RTT, latency will be perfect, but throughput will be horrible, right? So different protocols exhibit different trade-offs. So what you see here is that Cubic gets really high throughput, but it's loss-based, right? So the latency is horrible. PCC v1, which didn't incorporate latency, and actually even once you did incorporate latency, it didn't actually do that well, is not much better in that respect. BBR is better, but still suffers a 1 second latency. Vegas, I would say, is a better trade-off. And Sprout is a protocol from MIT designed specifically for this context, which I think is probably the optimum trade-off in this in this figure at least. I don't know how close it is to the optimum in general, but it's important to know that it's specifically for this context and also requires changes on both sides, right? It's like explicit receiver feedback. So you can see that PCC Vivace attains more or less the same level of self-inflicted latency and the somewhat lower throughput. Yeah. Okay, so there's more things you can look at. There's various demos. There's additional reading material. Thanks. So we're still very actively working on this, both on the algorithmic side and on the implementation side. So we're still seeking better online learning and utility frameworks. I think that PCC v2 Vivace is a step in the right direction, but I think that there's much more to explore. There's the question of how this should be adapted to mobile networks. There's the question of what the interface with the application should be. Like, what would video-aware PCC look like? And one thing we're working on now is building an open source consortium that will center around an implementation in Iccrg and a PCC kernel module. There's a lot of more details in the paper, including all the different parameters of the different simulation, emulation, and empirical results I've presented. And that's basically it. Thank you very much.
Matt Mathis, I was trying to figure out your question about why BBR did so poorly in that one graph. And I realized that BBR has in it an explicit assumption that the min RTT is stationary. And just varying the min RTT on a 5-second steps time intervals is guaranteed to screw up BBR. One of the things that we haven't done yet, which is going to come up at some point eventually, is how badly do we screw things like Leo. But in terrestrial routes, this is sort of an unrealistic scenario.
Thank you.
Hi, Bob Briscoe. Thank you very much for all that. I've got a question about the switch. Well, I think it was a switch partway through from selfish utility maximizing to everyone uses the same utility function. Is that true, or do?
From selfish utility maximizing to everyone uses the same utility function?
Well, you started talking about what utility function would be best for everyone.
Right.
Yeah.
Right. So in PCC v1, we've hardwired a specific utility function into the protocol. And we chose that specific utility function because we could show both formally and empirically that you get good equilibria, right, in this non-cooperative game that's induced by it. And in PCC v2, one of the things we've managed to do was to allow you to tweak your utility function without compromising convergence. So you no longer have to, there's different knobs in the utility function that reflect how much you care about latency, how much you care about goodput. You can play with these knobs and not compromise stability.
Okay, so my specific question was that if one cares about throughput and latency, and another cares about throughput and not latency, surely that one that doesn't care about latency is going to cause the other one to keep starving itself. And then it'll have to compromise the latency eventually if it wants some throughput, which is sort of the whole problem that Vegas had and everyone else has.
Right.
Yeah.
So I think that goes beyond PCC. As you note, that's inherent, right? Yeah. That is, you can play with the utility values, but this is but what you're basically doing is you're choosing a different balance of how much you care about loss and how much you care about latency as a signal.
Yeah.
Right. And that I agree. If you ignore latency completely, you'll end up taking over all the buffers. And
this is sort of why it given that latency, if you don't care about it, it also doesn't matter if you don't have it. In other words, having low latency is, even if you don't care about it, it's good for everyone else.
Right.
So there you do need to somehow design the thing so that you keep the latency low as long as you don't compromise your own utility function, just for everyone else that does want low latency. Yeah.
Yeah.
Yeah. Okay.
the same thing applies to, right.
Praveen from Microsoft. One question I had was, you showed the optimal rate
Yes.
in retrospect. How did you come up with that?
So if you know exactly the network parameters, right, then you can figure out, you know what the bandwidth is, you know what the RTT is, right, and you also know what the loss rate is. Right, so that means that you can try to operate at the exact operating point where you're fully utilizing the bandwidth and you're not going into the buffer.
Okay, but if you had multiple flows with different utility functions, would you still be able to compute this instantaneously, like in a later, after the run?
Oh, if you had multiple flows and you were playing with the emulated links, that's a good question. What you could compute is their fair share at each and every given point in time. So you could argue that ideally, right, they would be, let's say that it's 5-second intervals. So they actually do have enough time to converge. So most of that time, you would want them to spend at exactly their fair share of the optimum.
Okay. One thing that is interesting here is that because you have added now latency as a part of the utility function, is that less than best effort congestion control, like LEDBAT, it would be a good test of whether the utility function can mimic something like less than best effort. So that would be a very good test to do for this.
So that's a very interesting point. So we haven't actually, it's an interesting research question. We haven't actually tried seeing whether we can emulate other protocols well by choosing utility functions that match them.
Yeah.
But I think for LEDBAT, right, where you want to do best effort until someone enters, right? I think that is something that you could actually probably capture. One other thing I want to note about the utility function, which I think relates to one of the previous questions, is if you're loss-based, purely loss-based, then you're aggressive towards legacy TCP. If you're purely latency-based, right, then cubic might kill you, right? But because you have this utility function where you can play with the different parameters, you can strike the right balance between the two. Because I didn't talk about TCP friendliness, right, which relates to your question. But what we actually show in the paper, and we discussed TCP friendliness, is that even the purely latency sensitive Vivace that performs better than cubic in the wild. Because even though cubic is supposed to kill it, right? But I guess there's enough spare capacity for it to gain.
Sure. I think this kind of ties in very well with applications that want to pick their utility function. Like there are scenarios where you want to make that trade-off, but like this goes back to like Bob's question on what should be the default, because most applications today are not providing that information. So what would you pick as the default to do the best on the network?
So in the paper, we had two default choices. One that's loss-based and the other that's latency-based. In an ideal world, everything would be the PCC Vivace latency, I think, in terms of the utility function to choose to build into PCC Vivace. And you actually get good results for both. So I would argue the one that cares about latency is one that won't end up filling up buffers. So that's the one you would probably want globally.
Thank you.
Morteza from UCL. I have two quick questions. First, all of the experience that you are showing us is 5-second info, right?
In these specific.
What if 1 second or less than that?
So
because when the network becomes highly dynamic, right? All of those learning things that you're talking about doesn't work.
So I think that there's two issues here. One thing that we're currently exploring is the behavior of PCC. So this is joint work with Huawei that implemented this as a kernel module, and the behavior of PCC in mobile networks,
right?
Which I think is exactly what you're talking about.
Not about mobile networks, so we might have some dynamic
where the RTT might be way too slow to react, and you can actually get significantly better results than the existing protocols, because unless you have in-network cooperation, right? This is not a question of online learning, right? Unless you have in-network feedback, you're going to react at the time scale of an RTT. And now the question is, what do you do? And I would argue that online learning is what you should do in that context. You shouldn't hardwire responses regardless.
So what is my concern is, so you ended up with a rate, right? Which you think that is the right rate. And the network have a transient congestion, right? So when the transient congestion happens, your sending rate is quite high comparison with other flows which react quickly to the transient congestion. So you're going to be taking all of the bandwidth. So you are sort of penalizing, when the network becomes highly dynamic, you are penalizing other flows, competing flows, which are non-PCC flows, right? So this is my concept, rather than the online layering. So I'm worried about the rates that you think that is maximizing the utility functions. And at that time, network become, you are in the highly dynamic network.
Yeah.
Then the sending rate that you think is right, maybe is too aggressive to the competing flows. So,
but I think that isn't, that is dependent on your choice of utility function.
right.
So take, for example, a choice where you shy away from latency increase no matter what, right? In that scenario, you wouldn't be sufficiently aggressive, right? So this is a matter of figuring out what the right utility function is.
Okay, my second question is, have you considered any processing costs for this algorithm to run? Because in my past experience, you require a lot of CPU to work.
So we've actually, there's a few variants of kernel modules of this at this time. And one thing that we've done, and we owe Google a big thank you for that, is we've leveraged the changes that BBR have inserted into the module. And I think in that respect, the costs are approximately the same.
Thank you.
Yucheng Chen from Google. I love the PCC work. In fact, internally, we often compare PCC with BBR. And yes, there are a lot of similarities and there are differences. I want to ask for the utility function, have you considered beyond the RTT rate and loss, like application level metric? For example, videos probably care about the quality of experience the most.
So we've started considering this. I think it's a very important research direction. Right now, we focused on transport layer metrics, but I think, and there's some deployability issues here as well, because you may need the client's cooperation, right, to reveal some statistics, but maybe you can infer them from the sender as well. So I think it's a very interesting direction. We have not yet plugged in a utility function that reflects the quality of experience of the client. I think that would be great to do.
Yeah, I think a lot of video clients actually can sort of feed the quality of QoE metrics easily. So that would be very interesting. The other is also a similar question, that have you considered beyond the transport layer, but also beyond the flow level control? For example, if you ask a data center application what they care about the most, they would tell you it's the tail latency of my RPCs across 10,000 connections. I don't really care about your flow level thing. I only care about the last one, the straggler issues.
So
can we build a congestion control using your framework, but it's not just managing per flow, but looking at a little bit like the co-flow kind of concept from Berkeley, to say, can we build a congestion control that optimizes tail latency for a particular job?
We have not done that, but it seems like you could apply the same ideas. But I think it's worth exploring. We haven't done that. We have looked at what PCC might look like in a data center environment. Because if you wanted to incorporate ECN, and if you wanted to incorporate receiver feedback, but you're talking about a different angle. So,
yeah, because application usually they use flows as just channels, and they would spread their requests among a pool of connections. So to them, optimizing per flow is really the least of their interest. Yeah.
But I don't see a reason why we shouldn't be able to incorporate co-flow information. But that is something we should definitely explore.
Okay. Thank you.
Sorry, Spencer Dawkins is wearing a few hats, and it probably doesn't matter which one. This one is right now. I have a question, probably in the form of a suggestion, which, take it for what it's worth. And please don't try to answer it right now, because I hate people who blow up your presentation with a question that it's like no one would ever have thought of. The suggestion was, I wonder when you all will be ready to look at things like PCC with the kind of rich understanding of what you are running into for a modern protocol like Quick, which my first BOF in 2002 got shut down because we couldn't tell the difference between loss and congestion. And, some things remain constant over, decades. And that's one of them. So like I said, I ask you to consider that, but maybe more broadly for the group here, not the next IETF, but in the next year or two, is to be thinking, people have been working on TCP for a long time because TCP is TCP and everything. Basically everything else is either UDP or blocked at firewalls, but we're trying in the transport area in the IETF to get to the point where you can roll new protocols without having to upgrade operating system kernels and without having to upgrade middle boxes and stuff like that. And you can roll new congestion control mechanisms. And I would offer that as a possibility. I would also offer as a possibility thinking if the internet is a big place, right? So it's actually hard to work. It's hard to make big improvements on something that smart people have been trying to fix for 40 years. But are there specific corners of the internet where what you're thinking about would be more valuable than other corners? And is there a way for you to isolate what you're trying to do to those kind of corners? I have some theories about that. It doesn't matter, it doesn't matter what they are, and smarter people in the room could probably give you twice as good a theory over lunch. But as a transport, I can put that on for a second. As a transport area director, I would like for people who are thinking about research to be thinking about stuff that's more than the next operating system update, which a couple of year of time frame, but we're going to have an internet for a long time, and I know that ICCRG is schizophrenic, and it was before Jana was here, because we rely on ICCRG so much for guidance in the IETF. But and please don't stop doing that, because the internet is a big place, and there is, we'll probably be running TCP next week too. But to be maybe a little bit more schizophrenic and say, what are we looking at that's relatively short term and has to work everywhere, because something's going to, be blunt, something's going to go in the Linux kernel and it's not going to know. Or it's not going to get deployed at all. Like Cubic. That was the deal, right? You put Cubic in the Linux kernel, and then it has no idea who's trying to talk to it or from where. So that's a use case. And just thinking, especially if you guys are talking about like really different kinds of congestion control mechanisms like BBR and PCC and the next 5 that somebody will come in and want to talk to Jana about. Maybe that's something that's worthy of really smart people time in the research community as well. And thank you for letting me decide which hat I was wearing.
Thank you.
Just for the record, Allison's not in here, and my co-AD just left before I was in the mic line, so I'm completely unsupervised at this point.
We could. You're telling me now that I could turn this into whatever I want and nobody will know? Go on.
Okay, so my name is Nicolas Kuhn. I'm working for CNES, which is the French National Space Agency. And when I looked your curves on the comparison with your proposal and other optimized TCP versions, I have to say that when we have 10 megabytes links, we can actually get that capacity. So just that's the other side where you say that you have 17 more capacity with your proposal.
So which one? I'm sorry. So
if you go up in your presentation, have again, Up and down.
Oh,
The other way around, sorry. That's it. 17. I look at the paper, and basically you compare that with IBLA, which is not deployed in PEPs, and we have specific things. So basically, you may want to revise this message. Because I don't like saying that this curve with 10 megabytes and satellite only 1, and we can achieve that if you have a 10 megabytes link.
So I'd be happy to take this offline, because it'd be interesting to
Yes,
compare
I mean, I would be
to the
happy
benchmark you have in mind.
And another, that was a comment, and I have a small question on how you actually evaluate the loss rate.
The loss rate?
Yeah.
So we're using selective acts.
Okay, so you assume selective exact on the
So
other side.
we're using selective acts, and we use that because cumulative is just not enough to,
Exactly.
to gain
and also
statistics velocity.
and also the problem that with selective NACs, you may not be sure that you have actually losses, because packets may be, we use lots of layer 2 in transmissions, such as in cellular networks, and those are packets that are being transmitted, they are not lost due to congestion. So that is,
Yeah.
I mean,
so right
you
now,
may want to consider that, and I don't know how you can basically, in your models, consider that the measures you have may be incorrect, and see if that is resilient or not.
So this is a very good point. So right now, one thing we're looking at very closely is really mobile networks and satellite networks and the specific characteristics. So yeah,
So if you
I'd be very happy.
we have platforms if you want to try your thing on our real satellite links.
Cool.
So we can take that offline if you want.
I'll ping you after.
Okay, cool. Thank you.
Well, thank you so much.
Thank you very much.
This was the session goes on until 12, right? Oh, good Lord. Apologies. My sincere apologies. This is me basically without adult supervision. This is why we need ADs and well then that's it, folks. I'm going to have to apologize to the last presenter that we don't have the 10 minutes to do the presentation. I'm sorry. You had a chance to do this in DCPM, so I'm not going to feel that bad. Well, we'll see you all next time. Thank you. How did everything said, my agenda said 12. Nobody called it. Oh, hey.